we will now discuss the variation method. And this is extremely useful, and in fact this is the method that is used in all the calculations that, or almost all the calculations that people have been doing. If you go to the computer center, they would have packages which will enable you to calculate electronic structure of molecules. Programs like Gaussian or Gamers or other packages are there. They are all based upon this method, the variation method. Now, most of the time what happens is that, you see, we are not interested in all the solutions of the Schrodinger equation. I mean, of course, getting all the solutions would be very nice, but the thing is, most of the time we are interested in the ground state of the system. For example, suppose I have two hydrogen atoms, I bring together these two hydrogen atoms, they are in the ground state and I bring them slowly, so they will interact, but I move them so slowly that they interact and they are still in the ground state. And I want to calculate what happens to the energy of the system as I bring the two hydrogen atoms together. Would the energy decrease? If it decreased, there will be the formation of a bond, or would the energy increase, in which case there will not be the formation of any bond. So this is particularly in the ground state. Of course, I mean, I can say, okay, one of the hydrogens is excited and then I will bring them together. But that is not what you normally have in chemical problems. Normally things are in the ground state and they interact, okay, in the lowest possible electronic state. I should be very clear about this. So therefore, what is the thing? I mean, I have this equation Hi is equal to Hsi, and this H, well, on purpose we have been looking at systems for which H is sufficiently simple. If you had an atom like helium atom, you should remember that there are 3 particles in helium atom, the nucleus and the 2 electrons, but maybe I can get rid of center of mass motion of the system as a whole. This is we have already discussed. So therefore, it is effectively the relative motion of the 2 electrons with respect to the nucleus that is of great interest if you are a chemist. A helium like atom means that it has 2 electrons and a nuclear charge of plus Ze. So this is the nucleus having a charge of plus Ze, and there are 2 electrons, 1 and 2, both of which of course are negatively charged. So they have charges of minus E each. Now, as I said, we are not going to worry about center of mass motion. That means I will take the coordinate system in such a fashion that the nucleus is sitting at the origin, and then if I think of the Hamiltonian, you see you have H given by the expression which I will write now. This first electron is moving, so it has kinetic energy, and therefore associated with that I shall have the operator minus h cross square by 2m del 1 square. Del 1 square means I am differentiating partially with respect to the coordinates of electron 1. There are 3 coordinates. So this involves 3 partial differentiations, and then I would also have the kinetic energy of second electron, which gives me another operator minus h cross square by 2m del 2 square. Again 3 partial differentiations with respect to the coordinates of the second electron, and then I have to worry about the potential energy of the system. So electron 1 will interact with the nucleus. Let me call this distance r1. That interaction energy will be attractive, and therefore I shall have a negative sign. It will be given by minus Z E square divided by 4 pi epsilon 0 r1. Okay. Minus Z E square comes because the nuclear charge is plus Z and the charge on the electron is minus E. So minus E into Z square will give me minus Z square. Similarly, electron 2 will interact with the nucleus. If I denote that distance as R2, then that will give me a term which will read like minus Z E square divided by 4 pi epsilon 0 are 2. And not only that, you see the 2 electrons, they have the same kind of charge, as a result of which they repel each other. So, let us denote this distance as R12, and so the repulsive interaction, because it is repulsive interaction, it increases the energy of the system, and therefore, I have a plus sign here, plus E square divided by 4 pi epsilon 0 R12. So, this is the full Hamiltonian for the system. And as I have already told you, there are 6 partial differentiations involved in this operator. So, if you look at the Schrodinger equation, which would be H I is equal to E psi, and this is a partial differential equation involving 6 variables, extremely difficult to solve. In fact, one should perhaps say impossible to solve. But as I said, we would like to get some idea of the energy of the ground state if possible. The mathematical difficulties involved in solving this are enormous. People have tried to solve this equation exactly. I think even now there must be a few people, few scientists trying to solve this equation, but I suspect that nobody in the right senses would do it, because this is such a difficult thing. Of course, I mean, having said that, probably that is not a very careful statement, because if you can solve this equation, you will become very, very famous, right. And what I told should not discourage you from trying to solve it, okay. But I doubt whether it can be solved. Anyway, now the mathematical difficulties are enormous, and therefore, I cannot solve it. So, then at least I would like to know the ground state energy roughly, at least if possible. Can I have a procedure which will enable me to estimate the ground state energy of the system? This is the question. So, what I want to do is I want to get an expression for energy. So, how am I going to get an expression for energy? I have this equation H I is equal to E psi. This is not of great use because I cannot solve it, but what I am going to do is I am going to multiply both the sides by psi star, right. Even though I do not know what psi is, I can always imagine that I multiply by psi star and then integrate over the entire space. Now, what is d2? Well, you see, if you are thinking of helium atom, d2 will contain dx1, dy1, dz1, dx2, dy2, dz2. Remember that. So, therefore, depending upon what your problem is, d2 can be different. And this expression you can take and get another expression which looks nice. So, this is the expression that I get for E, right. Nice to look at, but totally useless expression. Why is it useless? It is of no use, simply because you see, you do not know what psi is. So, what is the fun in having such an expression for E, because after all you did not know psi, you do not know psi. Even if you knew psi, then why should you write this expression, because you can just say take that psi, put it here, allow S to be operated upon by, right, allow S to operate upon that psi, and you will get E. So, this is straightforward. So, therefore, as it stands, this is not a useful expression, you cannot think of any use for it, but that is something very interesting. Usually, if you have a physical system, our physical intuition will allow us to write down a wave function for the system which we think is approximately correct, right. I will show you how it can be done. So, let me say that I have an approximate wave function phi, which I am just guessing, right, and I suspect that phi is a fairly decent approximation to psi, and phi is not, because I have guessed it, right. And then what I will do is I will take this approximate function, and wherever psi occurs in here I can put that phi. So, what will I get? I will get an approximate energy. Right? You are not going to get the exact energy, that you will not get. So, you will get an energy which I will denote by this symbol. I shall refer to this as script E. It is not the normal way you write E, it is a little bit written differently, and therefore, I shall refer to that as script E. So, what do I expect? I expect that script E will be an approximation for the energy of the system. To be specific, I would imagine probably that if I was careful in choosing my wave function, it will be an approximation for the ground state energy. I mean, all that I need to do is I have to choose phi in such a fashion that there are no nodes, because I know the ground state wave function has no nodes. So, I can make use of that. Imagine that I have chosen phi in such a fashion that there are no nodes, then probably it will turn out to be an approximation for the ground state energy of the system. Okay. If that was all, then again this is not very interesting. You can actually prove that script E has to be greater than or equal to the ground state energy. This is what is very interesting. It does not matter what phi you use. I may have a phi, one of you may have a different phi. For both the phi's, right, my phi I will call phi mine, and your phi I will call phi yours. It is guaranteed that this put here or this put there, both will give you answers. They will not be the same, they will be different, but both are guaranteed to be greater than the actual ground state energy. Okay. And suppose you get two such values. Well, for the first one I get E mine, and the second I get E yours. Both are greater than E0. So, which one among these two will you choose as the better approximation? The one that is closer to E0, which one would that be? That will be the one which is lowest or which is lower among these two, right. So, even see, suppose this, I mean, as an example, suppose this turns out to be, I mean, let us say I am doing a calculation for hydrogen atom, and suppose this comes out to be minus 10 electron volt, and this comes out to be minus 11 electron volts, whereas the actual ground state energy of the hydrogen atom in the ground state is minus 13.2 electron volts. So, you can see what has happened, both of them are greater than minus 13.2, but the one that is lower, which is minus 11 electron volts, is the better approximation. So, therefore, I have a very quantitative way of estimating the goodness of wave functions. If I have a wave function and if you have a wave function, I can easily tell you all that I need to do is I do this calculation and find out which one gives me a lower energy, that is a better approximation, correct. And this is a very useful procedure. Now, to illustrate this procedure, actually I will take the example of a particle in a box, in a one dimensional box. So, here is my particle in a one dimensional box. The box goes from 0 to A. I actually know everything regarding this problem. I know the eigenfunctions, I know the eigenvalues and so on, but let me not worry, let me just say that okay, I do not know anything about these eigenfunctions and eigenvalues. I want to use an approximate wave function to calculate the energy of the ground state. But the information that we already have means that the ground state energy is actually E1 equal to n square pi square h cross square by 2 ma square with n equal to 1. So, this is the actual ground state energy of the system. If we solve the Schrodinger equation exactly, this is what is going to happen, correct. And now you see I do not want to follow that procedure. Essentially I want to illustrate the variational approach. So what I want to do is I want to guess a wave function for the system and use that guessed wave function to calculate the value of script E, correct. So how will I guess the function? Well, it is fairly simple in this case, because I know that you see here and there what should happen, the function, the wave function, I know it has to vanish at the boundaries of the box. You see, if the particle does not go beyond the boundaries of the box, because at the boundaries of the box you have infinitely high potential. So therefore at the boundaries of the box the wave function has to vanish, it has to vanish here, it also has to vanish there. So what is the simplest function that I can think of? What is the simplest phi? Phi has to be a function of x, but it has to vanish at x is equal to 0 as well as at x is equal to a. What is the simplest function that I can think of which will satisfy this criterion or will satisfy this requirements? The answer is that I can think of a function which may be something like x into a minus x, correct, because if you put x is equal to 0 the function will vanish, if you put x is equal to a again the function will vanish, and therefore this is the simplest function. You can think of any number of other functions, but this is the simplest one. And in fact if you plotted this function against x, how will it look like? It will be 0 here and it will increase, reach a maximum, and it will decrease. So that is how this function looks like. It has no nodes in between 0 and a. And now I want to calculate script E. What would script E be? Well, of course you see here x is between 0 and a. Remember that in that region the function is this, outside that region of course we know the particle does not go, so the wave function will be 0, even my phi will be 0 outside. So script E will be in integral what is the Hamiltonian? Well, minus h cross square divided by 2m d square upon dx square. This is the Hamiltonian operator for a particle in a one dimensional box. This is the Hamiltonian operator provided the particle is within the box. So therefore I would have my this operator operating upon my phi. So phi, then phi star, then dx integrated from 0 to a. That is all that is of interest to me. Because outside everything is 0, the function is 0. So and what do you have as the numerator? Sorry, as the denominator? It is going to be integral 0 to a phi star phi dx. This function, the way it is written, it is not normalized, so therefore I have to include this. If it was normalized, this would be equal to 1. So now fairly simple and straightforward to evaluate this. Okay, let me first evaluate this part, integral 0 to a phi star phi. After all, you see phi is a simple thing, phi star is phi itself. So therefore it is nothing but x square into a minus x the whole square into dx. That is all this is, the denominator, and this will be equal to integral 0 to a dx quickly. Simple. Let me do the integral and get the answer. Well, please follow carefully, because I do not want to be making a mistake. I think this is okay. So, we have evaluated that part. The what is left is the other part. Integral of 0 to a dx into x minus a minus x minus h cross square by 2m. I will take it outside. D square upon dx square x into a minus x is equal to minus h cross square by 2m integral 0 to a dx x into a minus x. You have to evaluate the second derivative of this object, very simple, because the first term is ax, second derivative is 0, the second term is minus x square, second derivative is minus 2. So, therefore, this minus 2 can be taken in outside. You will get h cross square divided by m integral 0 to a dx into ax minus x square, that is equal to h cross square by m ax square by 2 minus right. This is the final answer. Therefore, what has happened is script E will be equal to, tell me if there is any mistake, h cross square divided by 6m, an a cube is missing, as it always happens with me. So, a cube divided by 1 by 30 a to the power of 5. So, what is the answer that I get? This is the final answer, correct? Okay, you can verify this, because I want to finish in a few minutes. So, this I may write as 10 h cross square divided by 2 m a square. So, the result of all these calculations, which are not difficult, but maybe perhaps tedious, what has turned out is that script E is how much? 10 h cross square divided by 2 m a square. This is your value of script E using this very approximate wave function, which we just guessed. All that we used was that the function should vanish at the boundaries of the box, that is all. And if you look at the actual expression, what happens? Instead of this 10, you have pi square, that is all. So, pi you know is 3.1415 etc. So, if we calculated the value of pi square, pi square would be approximately 9.84. I mean, there are, this is approximate, that it may be 9.85. Do the calculation, you will find it. So, instead of the actual 9.84, what did I obtain? I obtained 10. What is the percentage of error I have got in this calculation? It is only 1.6 or 1.5%, correct, because 10 and 9.84, right, the percentage of error is only 1.5%. So, even this rather crude calculation gives me a fairly decent value for the energy, right. And not only that, this energy that you obtain, it is 10, it is greater than the actual energy, which substantiates the variation theorem. So, in my next lecture, what I will do is, I will prove the variation theorem, which says that script E is greater than or equal to the actual ground state energy. This is known as the variation theorem. Script E, I will prove that it has to be greater than or equal to the actual ground state energy, and then discuss some applications of the variation method. Okay, thank you.